Hello, sleepy genius. Another day has passed, and here you are, seeking refuge in the quiet hours. Let your thoughts settle like snow on frozen ground. Tonight, we turn our gaze toward one of nature's most ethereal performances, painted across the polar heavens. Rest now, and let wonder carry you gently into sleep. From ancient warriors seeing bridges to the afterlife, to solar particles colliding with our atmosphere at millions of miles per hour, the northern lights have danced above us for billions of years. Indigenous peoples called them the spirits of ancestors. Vikings believed they were reflections from the shields of the Valkyries. Tonight, we follow the science behind this celestial ballet that transforms darkness into rivers of luminous color. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please, share your thoughts below. Now, let's begin. The aurora borealis occurs when charged particles from the sun collide with gases in Earth's atmosphere at altitudes between 60 and 200 miles above the surface. Imagine standing beneath a night sky where invisible forces are painting with light itself. Electrons racing at speeds exceeding 45 million miles per hour. Scientists discovered in 1896 that Norwegian physicist Christian Birkeland first proposed that the lights were caused by currents from the sun exciting particles in our upper atmosphere. He conducted experiments in his laboratory using Torella, magnetized spheres that simulated Earth's magnetic field. In 1967, satellites confirmed his theory when they detected streams of solar wind interacting with Earth's magnetosphere. To think that what appears as gentle curtains of light represents one of the most violent interactions between our planet and the sun. The green color that dominates most auroral displays comes from oxygen molecules located approximately 60 to 150 miles above Earth's surface. Picture a moment when a single atom of oxygen absorbs energy from a solar electron, holds it for nearly 1 second, then releases it as a photon of green light at a wavelength of 557.7 nanometers. Research from the University of Alaska Fairbanks in 2008 showed that this specific shade of green occurs because oxygen takes about 0.7 seconds to emit light after excitation. At lower altitudes, where oxygen is denser, collisions happen too quickly for this emission to occur. At higher altitudes, the rarer oxygen produces red light at 630 nanometers instead. NASA's Themis mission in 2007 documented that these emissions create a glow bright enough to read by during intense displays. This reminds us that even the air we breathe becomes luminous when touched by the cosmos. Japanese historical records document auroras appearing over Kyoto between 1770 and 1771. Events so rare they were considered miracles. Imagine court officials in feudal Japan watching red lights spread across the northern horizon, a phenomenon appearing in records only a few times per century. Historical analysis, published in 2017, examined these records and determined they correspond with the strongest geomagnetic storms of the 18th century. Chinese annals, dating back to 2000 BC, contain descriptions of light ki in the northern sky, possibly referring to auroral displays. Korean records from the Joseon dynasty describe more than 1,700 auroral observations between 1392 and 1910, providing scientists with valuable data about long-term solar activity patterns. In 2019, researchers compared East Asian auroral records with European ones, finding that many major displays were recorded by multiple independent civilizations, confirming their global nature. This reminds us that the same lights witnessed across cultures and centuries bind human history together. A shared spectacle connecting observers separated by time and distance. The red aurora appears at altitudes above 150 miles, where oxygen is less dense and takes longer to emit light after excitation. Imagine the patience required for an oxygen atom to hold on to its energy for up to 2 full minutes before releasing it as crimson light. Scientists at the European Space Agency discovered in 2001 that red auroras are rarer because these high-altitude collisions require more energetic solar storms. During the Great Geomagnetic Storm of March 1989, red auroras were visible as far south as Texas and Florida. Witnesses described the sky as though it were on fire, with blood-red curtains extending from horizon to horizon. To think that color itself is just matter, remembering a collision that happened minutes before. Medieval European accounts describe the aurora as signs of divine anger or portents of war and famine. Imagine chroniclers in monasteries recording blood-red lights in the sky, interpreting them through theological frameworks as warnings from God. The Anglo-Saxon Chronicle records auroral displays in 793 AD, describing them as fiery dragons flying in the air that preceded the Viking raid on Lindisfarne. In 1583, auroras visible across Europe were interpreted as omens of plague and war, descriptions that proved coincidentally accurate when plague struck months later. Renaissance scholars debated whether auroras were atmospheric phenomena or celestial, with most favoring atmospheric explanations. Galileo coined the term aurora borealis in 1619, naming it after Aurora, the Roman goddess of dawn, and Boreas, the god of north wind. To think that we saw catastrophe in beauty, that lights which harm nothing were feared as harbingers of destruction, revealing how urgently humans seek meaning in celestial events. Nitrogen molecules produce blue and purple hues in the aurora, typically appearing at the lower edges of auroral displays. Picture nitrogen being struck by solar particles at altitudes below 60 miles, ionizing instantly and releasing light at wavelengths between 391 and 470 nanometers. Research from 2012 at the University of Oslo showed that blue auroras indicate particularly strong solar activity because nitrogen requires more energy to excite than oxygen. During the Carrington event of 1859, telegraph operators reported seeing brilliant purple and blue auroras so bright they could see to read newspaper at midnight. One operator in Boston disconnected his batteries and sent messages solely using the electrical current induced by the aurora itself. In a sense, the atmosphere becomes a lamp with no filament, lit by an invisible hand millions of miles away. The aurora australis, or southern lights, mirrors the northern lights almost perfectly in the opposite hemisphere. Imagine 2 luminous wreaths encircling Earth's poles simultaneously, like symmetrical crowns worn by the planet itself. Scientists discovered in 1902 that Norwegian explorer Roald Amundsen first documented the southern lights during his Antarctic expeditions, noting they appeared identical in color and form to those in the Arctic. Research from 2009, using simultaneous satellite observations, confirmed that both auroras pulse and shift in near-perfect synchronization. In March 2015, astronauts aboard the International Space Station photographed both auroras at once, revealing Earth wrapped in twin bands of shimmering green. This reminds us that beauty often comes in pairs, balanced across the geometry of our spinning world. Traditional Inuit knowledge describes the aurora as spirits playing ball with a walrus skull or as ancestors lighting torches to guide travelers. Imagine generations of Arctic peoples watching these lights and weaving them into the fabric of their worldview, creating explanations that served both practical and spiritual purposes. Ethnographic research from the early 1900s recorded that some Inuit groups believed whistling at the aurora would attract it closer, while others thought the lights could steal children who stayed outside too long. In northern Quebec, Inuit hunters traditionally used auroral predictions as weather indicators, noting that certain auroral patterns preceded storms. Scientists working with indigenous communities in Alaska have found that traditional observations of auroral frequency and intensity correlate with sunspot cycle variations, suggesting centuries of systematic observation. This reminds us that before satellites and magnetometers, humans watched the same sky and found patterns, building knowledge systems that sustained life in Earth's harshest environments. The aurora produces sound, though scientists debated its existence for centuries before confirming it in 2012. Picture standing beneath shimmering curtains of light and hearing faint claps, crackles, and whooshing sounds, like distant fireworks or silk being torn. Finnish researchers at Aalto University recorded these sounds in 2012 and determined they originate from electrical discharges at altitudes around 230 feet, far below the visible aurora. Research showed that temperature inversions in the atmosphere create layers where electrical charges accumulate, then discharge audibly when disturbed by geomagnetic activity. Indigenous peoples in northern Canada have described these sounds for thousands of years, calling them the voices of spirits. To think that we doubted our ancestors' ears for so long, only to discover they were hearing something real that science simply hadn't yet measured. The aurora borealis received its name from an Italian astronomer who never witnessed the phenomenon firsthand. Consider Galileo Galilei in 1621, sitting in his study in Florence, reading accounts of mysterious lights seen across northern Europe. He combined Aurora, Roman goddess of the dawn, with Boreas, god of the north wind, creating a name that would endure for centuries. Research from the Galileo Museum in Florence revealed in 2003 that Galilei chose this name because early observers described the lights as resembling dawn breaking along the northern horizon. Historical analysis shows that Mediterranean cultures rarely witnessed auroras, making them exotic mysteries described in travelers' tales. To think that one of history's greatest observers named a phenomenon he never saw, building poetry from second-hand accounts. The magnetic pole and geographic pole are separated by more than 300 miles, and this distance changes constantly. Picture the magnetic North Pole wandering across the Canadian Arctic at speeds exceeding 30 miles per year. Faster now than at any point in recorded history. Scientists at the British Geological Survey discovered in 2019 that the pole has accelerated from 9 miles per year in the 1990s to nearly 34 miles per year by 2019. Research published in Nature in 2020 showed that this acceleration is caused by competing magnetic blobs deep within Earth's liquid outer core. In 2001, the magnetic North Pole crossed into the Arctic Ocean, leaving Canadian territory for the first time in centuries. This reminds us that Earth's magnetic heart is restless, drifting according to currents of molten iron we will never see. The thickness of an auroral curtain is less than 300 feet, thinner than many clouds, yet stretching for hundreds of miles. Imagine a sheet of light so thin you could walk through it in seconds, yet so tall it extends from 60 miles altitude to beyond 600 miles. Scientists discovered in 1998 at the University of Alaska that rocket flights through auroral curtains measured their width using electric field sensors. Research from 2007 showed that curtains maintain their thinness because electrons are focused into narrow beams by electric fields in the magnetosphere. During one research flight in 2004, instruments detected the transition from darkness to bright aurora and back to darkness in under 4 seconds, revealing the curtain was only 180 feet thick. To think that such immense vertical structures maintain edges sharper than most clouds, boundaries between light and dark measured in tens of meters. The temperature inside an auroral display can exceed 2,700 degrees Fahrenheit, yet you would feel nothing standing beneath it. Picture air molecules heated to temperatures that would vaporize steel, floating 60 miles above your head in atmosphere so thin that heat has almost no meaning. Research from 2005 at the Norwegian Space Center showed that during intense auroral activity, atmospheric temperature at auroral altitudes can rise by more than 1,800 degrees within minutes. Scientists discovered that despite these extreme temperatures, the air is so rarefied that total heat energy remains negligible. A human standing at auroral altitude would freeze from lack of atmospheric pressure long before noticing any warmth. This reminds us that temperature without density is phantom heat, numbers that describe molecular violence in a realm too empty to burn. Auroral photons travel for only 10 nanoseconds before your eye captures them. Imagine light born 60 miles above you, created when an electron strikes oxygen. That photon racing downward at 186,000 miles per second, reaching your retina in less time than a hummingbird's wings beat once. Scientists calculated in 2011 that an observer seeing an aurora is receiving photons that didn't exist 1/10,000,000th of a second earlier. Research from the University of Oslo showed that some auroral photons are absorbed and re-emitted by atmospheric molecules multiple times before reaching ground level. During intense displays, your eyes capture billions of these newborn photons every second. To think that what you see is younger than your thoughts about seeing it. Light created and perceived in time frames our consciousness cannot grasp. The auroral oval is a permanent ring of light encircling each magnetic pole, expanding and contracting with solar activity. Picture an invisible crown hovering above the Arctic, typically centered over northern Canada and Siberia rather than the geographic North Pole. Research from the Polar Satellite in 1996 showed that this oval sits about 15 to 25 degrees from the magnetic pole and moves throughout the day as Earth rotates beneath it. During quiet solar periods, the oval spans about 3,000 miles in diameter. During geomagnetic storms, it can expand to more than 5,000 miles, bringing auroras to latitudes as low as the Mediterranean. In 1909, explorers near the geographic North Pole reported no auroral activity, while simultaneously displays lit the skies over Norway. To think that the poles we see on maps are not where Earth's magnetic heart truly resides. Solar wind travels from the Sun to Earth at speeds averaging 250 miles per second, taking approximately 2 to 4 days to reach our planet. Imagine a river of charged particles, mostly electrons and protons, flowing constantly outward from the Sun's corona in all directions. Scientists discovered in 1958 that physicist Eugene Parker first predicted this solar wind's existence, though many colleagues dismissed his theory as impossible. In 1962, NASA's Mariner 2 spacecraft confirmed Parker's prediction during its journey to Venus, measuring wind speeds and particle densities. The Apollo astronauts traveling to the Moon in the 1960s passed through this wind, protected only by their spacecraft walls. This reminds us that we live inside our star's atmosphere, Earth floating in an invisible stream that never stops flowing. Coronal mass ejections are massive eruptions of plasma from the sun's surface that can hurl billions of tons of matter into space. Picture the sun's outer atmosphere suddenly tearing away, releasing a cloud of magnetized particles larger than Jupiter itself, racing toward Earth at speeds up to 3,000 miles per second. Research from NASA's Solar Dynamics Observatory in 2012 showed that the sun releases these ejections regularly, though most miss Earth entirely. On July 23, 2012, a massive ejection passed through Earth's orbit, missing our planet by just 9 days. Scientists estimated that if it had struck Earth, the resulting geomagnetic storm would have been comparable to the Carrington event, potentially causing trillions of dollars in damage to power grids and satellites. To think that we are always 1 week away from a cosmic event that could return us to the pre-electric age. The Carrington event of September 1859 remains the most powerful geomagnetic storm ever recorded in human history. Imagine telegraph wires sparking and catching fire spontaneously, operators receiving electric shocks, and messages being sent with batteries completely disconnected. British astronomer Richard Carrington was observing sunspots on September 1, 1859, when he witnessed a massive solar flare, the first ever recorded. 18 hours later, auroras appeared worldwide, visible at tropical latitudes including Cuba, Hawaii, and Colombia. In the Rocky Mountains, gold miners woke at 1 a.m. thinking it was dawn and began preparing breakfast. One telegraph operator in Washington, D.C. continued sending messages for 2 hours using only the current induced by the storm. To think that our sun, so constant and predictable, can occasionally unleash fury that makes our technology seem as fragile as candle flame. The Sami people of northern Scandinavia traditionally treated the aurora with respect, tinged with fear, believing the lights were dangerous and should not be mocked. Imagine a culture developing taboos around auroral displays, teaching children never to wave at the lights or sing to them. Historical records from Finnish Lapland describe beliefs that the aurora could descend and harm those who disrespected it. Sami traditions held that the lights were reflections from massive shoals of herring, connecting auroral appearances with fishing predictions. In northern Norway, Sami shamans incorporated aurora observations into their divination practices, interpreting colors and movements as messages from the spirit world. Anthropologists note that these beliefs likely evolved from witnessing the rare occasions when auroral electric fields were strong, enough to be felt as static electricity, creating a rational basis for caution. To think that fear and wonder can intertwine so thoroughly that the boundary between them dissolves, and perhaps that combination is simply another word for respect. Earth's magnetosphere extends approximately 40,000 miles toward the Sun and stretches more than 200,000 miles in the opposite direction. Picture an invisible shield, shaped like a teardrop, constantly bending and compressing under the pressure of solar wind. Scientists discovered in 1958 that this magnetic field is generated by the motion of molten iron in Earth's outer core, spinning and convecting at depths of 1,800 miles beneath our feet. Research from NASA's Van Allen probes in 2013 showed that this shield prevents solar wind from stripping away our atmosphere, as happened to Mars billions of years ago. Without this protection, Earth would have lost its oceans to space long ago. This reminds us that the ground beneath us contains a dynamo that makes all life possible, turning iron into an invisible fortress. Magnetic reconnection is the process that powers auroral displays, occurring when magnetic field lines from the Sun connect with Earth's field and snap like rubber bands. Imagine two invisible force fields touching, merging, then explosively separating. converting magnetic energy into heat and kinetic energy in microseconds. Research from 2008 at NASA's Goddard Space Flight Center showed that during reconnection events, particles can be accelerated to nearly the speed of light in distances shorter than a football field. In July 2014, the magnetospheric multi-scale mission recorded reconnection happening in Earth's magnetospheric, measuring energy releases equivalent to thousands of nuclear weapons. Scientists observe that these events occur roughly every 3 minutes during active periods. To think that above our heads, fields we cannot see are constantly breaking and reforming, releasing power that lights the sky. Substorms are explosive releases of energy that occur every 2 to 3 hours during periods of auroral activity. Imagine the magnetosphere loading up with energy like a drawn bow, then suddenly releasing it all at once, causing auroras to brighten by factors of 100 or more within seconds. Scientists discovered in 1964 that physicist Shinichi Akasafu first described the substorm sequence after analyzing thousands of all-sky camera images. Research from the Themis satellite mission in 2008 pinpointed where substorms begin, roughly 20,000 miles above Earth in the magnetosphere. During a substorm, auroral arcs suddenly break up into swirling spirals and rapidly moving rays. In Fairbanks, Alaska, time-lapse cameras have captured substorms, transforming quiet green arcs into explosive coronas that fill the entire sky in under 2 minutes. This reminds us that even tranquil beauty contains violence, merely waiting for the right moment to reveal itself. Proton auroras are invisible to human eyes but create faint red glows detectable by sensitive cameras. Picture hydrogen atoms from the solar wind being stripped of their electrons, becoming protons that steal electrons from Earth's atmosphere as they descend. Research from 2007 at the University of Calgary showed that these proton auroras emit light primarily in the ultraviolet spectrum beyond human vision. During intense geomagnetic storms, proton auroras can extend across the entire polar region simultaneously. In 2003, the IMAGE satellite captured proton auroras spanning more than 3,000 miles across North America. Scientists noted that these auroras don't shimmer or move like electron auroras, but instead glow steadily, to think that above us, invisible to our eyes. Another kind of aurora burns continuously, a ghost light we can only see through machines. Auroral kilometric radiation is a powerful radio emission generated by auroras, though it cannot penetrate Earth's ionosphere to reach the ground. Imagine standing beneath an aurora while it screams in radio frequencies louder than Jupiter's radio emissions. Yet you hear nothing because the sound is trapped above you. Scientists discovered in 1979 that the ISEE spacecraft first detected these emissions from space, measuring power outputs reaching millions of watts. Research from NASA's WIND spacecraft in 2001 showed that this radiation is produced at altitudes between 2,500 and 15,000 miles by electrons spiraling along magnetic field lines. Radio astronomers have detected similar emissions from other planets, including Jupiter, Saturn, Uranus, and Neptune. This reminds us that the universe speaks in languages we cannot hear without translation, broadcasting messages that pass through us unnoticed. The auroral electrojet is a river of electrical current flowing through the ionosphere during auroral displays, carrying up to 1 million amperes. Picture an invisible river of electricity, 60 miles wide and stretching thousands of miles from dawn to dusk, flowing through the thin air above the Arctic. Research from 1972 showed that this current flows westward during the evening and eastward during the morning, following the auroral oval. Scientists at the University of Alaska discovered in 2005 that during intense geomagnetic storms, this electrojet can induce currents in power transmission lines strong enough to melt transformer cores. During the March 1989 storm, these induced currents caused the collapse of Quebec's power grid, leaving 6 million people without electricity for 9 hours. To think that light in the sky can reach down and touch our civilization, flowing through wires like water finding cracks in stone. Pulsating auroras are patches of light that brighten and dim rhythmically, typically with periods between 2 and 20 seconds. Imagine watching clouds of green light pulse like a heartbeat across the sky, breathing in synchrony as though alive. Scientists discovered in 2015 that these pulsations are caused by waves in Earth's magnetosphere, scattering electrons into the atmosphere in rhythmic bursts. Research from Japan's ARACE satellite in 2018 directly measured these chorus waves at their source, confirming they vibrate at frequencies between 100 and 6,000 Hz, similar to the range of human hearing. In December 2020, citizen scientists in Finland captured rare purple pulsating auroras on camera, a color combination previously undocumented. To think that the sky itself can pulse like a living thing, keeping time to invisible drums played in the vacuum of space. Black auroras are dark bands that appear within auroral displays, looking like holes torn in the luminous curtains. Picture watching light in the sky when suddenly a dark column appears, moving upward at speeds exceeding 6 miles per second. Research from 1983 at the University of Iowa showed that these aren't actually dark, but rather regions where fewer electrons are precipitating into the atmosphere. Scientists discovered in 1996 that black auroras indicate areas where electric fields are accelerating electrons parallel to magnetic field lines rather than perpendicular to them. During intense displays, these black bands can split auroral curtains into multiple ribbons. In 2001, high-speed cameras in Svalbard captured black auroras appearing and disappearing within fractions of a second. This reminds us that sometimes darkness teaches us as much as light, revealing the structure of invisible forces by their absence. STEVE, or strong thermal emission velocity enhancement, is a narrow purple ribbon that appears separately from typical auroral displays. Imagine a river of light, only 15 miles wide but stretching thousands of miles from east to west, glowing mauve and moving westward at speeds up to 4 miles per second. Citizen scientists in Alberta first documented STEVE in photographs taken in 2016, though the phenomenon had been observed for decades without understanding. Research from NASA in 2018 showed that STEVE is caused by a ribbon of hot gas flowing through the ionosphere at temperatures exceeding 5,400 degrees Fahrenheit. Scientists at the University of Calgary discovered that STEVE appears at lower latitudes than normal auroras and isn't caused by particle precipitation, but by a fast-moving stream of charged particles. To think that amateur photographers could discover a new atmospheric phenomenon that professional scientists had overlooked, reminding us that wonder still hides in plain sight. The picket fence aurora appears below STEVE as a series of green vertical columns resembling a fence stretching across the horizon. Picture thin green pillars of light, each about 6 miles wide, spaced evenly like the bars of a cosmic fence. Scientists discovered in 2019 that these structures are caused by electrons precipitating into the atmosphere in narrow beams. Research from the Swarm satellite constellation showed that the picket fence occurs at altitudes between 55 and 68 miles, lower than typical auroras. In March 2018, photographer Neil Zeller captured both STEVE and the picket fence simultaneously over Calgary. providing scientists with crucial data about their relationship. Measurements showed that the fence appears only when Steve is present. This reminds us that the sky contains structures of precise geometry, drawn with light according to rules we're only beginning to understand. Auroral beads appear as evenly spaced bright spots along auroral arcs, looking like pearls strung on an invisible thread. Imagine watching a green arc suddenly break into dozens of luminous beads, each about 6 miles in diameter, appearing simultaneously across thousands of miles. Research from 2016 at NASA's Goddard Space Flight Center showed that these beads form in the final moments before substorm onset, marking the transition from quiet to active aurora. Scientists discovered that the beads are spaced according to a mathematical relationship involving plasma properties in the magnetosphere. In August 2015, all sky cameras across Alaska captured the formation and evolution of auroral beads with unprecedented detail. The beads lasted only 10 to 20 seconds before the arc broke up into full substorm activity. To think that chaos announces itself with such perfect symmetry, geometry appearing in the instant before everything breaks apart. Dunes in the aurora are parallel wave-like structures discovered only in 2020 by Finnish citizen scientists. Picture horizontal waves rippling through green auroral light, each wave crest spaced exactly 28 miles from the next, extending for hundreds of miles. Researchers at the University of Helsinki analyzed photographs taken in January 2020 and determined that these dunes occur at altitudes around 62 miles. Scientists proposed that the dunes form where atmospheric waves in the mesosphere modulate the density of oxygen atoms, creating periodic variations in auroral brightness. This discovery revealed a previously unknown coupling between auroral processes and atmospheric waves. In a sense, we've been watching auroras for thousands of years, yet they continue surprising us with patterns that existed all along, waiting only for someone to notice and ask why. Theta auroras are rare auroral formations shaped like the Greek letter theta, with a bright spot at the magnetic pole surrounded by a ring of light. Imagine Earth wearing a luminous crown with a jewel at its center, visible only from space. Scientists discovered in 1986 that the Dynamics Explorer satellite first photographed a theta aurora during periods of northward-pointing interplanetary magnetic field. Research from 2005 showed that theta auroras occur less than 1% of the time but indicate unusual magnetic field configurations. During these events, solar wind particles enter Earth's magnetosphere through different pathways than during typical auroras. In September 2016, satellites captured a perfect theta aurora over the Arctic, lasting for more than 3 hours. To think that our planet occasionally wears such rare geometries, crowns that appear only when cosmic conditions align in uncommon ways. Double auroral ovals have been observed during extreme geomagnetic storms when 2 separate rings of aurora appear simultaneously. Picture looking north and seeing 2 complete rings of light, one inside the other, both pulsing and shifting independently. Scientists discovered in March 1989 that during the massive geomagnetic storm that blackened Quebec, satellites observed 2 distinct auroral ovals spanning the northern hemisphere. Research from 2003 showed that the outer oval forms when the magnetosphere becomes so compressed that a secondary boundary layer creates its own auroral zone. During the Halloween storms of 2003, astronauts aboard the International Space Station photographed double ovals from above, describing them as nested halos of green and red. This reminds us that even phenomena we think we understand can double themselves under extreme conditions, showing us they contain hidden layers. Auroral coronas appear when an observer stands directly beneath an aurora, making the light seem to radiate from a single point directly overhead. Imagine lying on your back and watching ribbons of light converge above you like looking up through a luminous tunnel. This perspective effect occurs because parallel auroral curtains appear to meet at a vanishing point due to perspective. In 1902, Norwegian physicist Christian Birkeland described coronas as the most magnificent auroral form. Research from 2011, using Ørsted cameras, showed that coronas indicate the observer is positioned directly beneath the auroral oval's center. During intense substorms, coronas can fill the entire visible sky, with rays appearing to shoot downward from a central point like cosmic rain. To think that our position on the ground determines whether we see curtains or cascades, the same light transformed by nothing more than where we choose to stand. The auroral curtain is the most common auroral form, appearing as vertical sheets of light that sway and ripple like fabric in wind. Picture silk curtains hanging from the sky, 600 miles long but only 100 yards thick, so thin that you could walk through one in seconds. Scientists discovered in 1967 that these curtains align precisely with Earth's magnetic field lines. Research from 2008 showed that auroral curtains mark boundaries where different populations of charged particles meet in the magnetosphere. High-speed cameras have captured curtains moving horizontally at speeds up to 6 miles per second while simultaneously rippling vertically. In Tromsø, Norway, researchers in 2015 flew rockets directly through auroral curtains, measuring electric fields stronger than 100 millivolts per meter. This reminds us that what appears as gentle fabric is actually a boundary layer between cosmic forces, as precisely structured as it is beautiful. Auroral rays are vertical structures within curtains, appearing as bright columns that extend upward along magnetic field lines. Imagine pillars of light shooting upward from the horizon, each one tracing an invisible line of force that connects ground to space. Research from 1998 at the University of Alaska showed that individual rays are typically less than 60 feet wide, though they can extend vertically for more than 600 miles. Scientists discovered that rays mark locations where the magnetic field is particularly strong or where electron beams are more focused. During intense displays, thousands of individual rays can appear simultaneously, creating what observers describe as a cosmic cathedral. In 1938, photographer Yuichi Takasaki captured auroral rays so detailed that scientists could measure their width and spacing from his images. To think that each ray is a path, an electron highway connecting our atmosphere to the vast magnetic rivers that flow through space. Auroral torches are isolated, rapidly moving bright spots that appear to fall from higher auroral structures like drops of light. Picture watching an auroral curtain when suddenly a bright spot detaches and falls downward at speeds exceeding 10 miles per second, fading as it descends. Scientists discovered in 1989 that these torches are caused by bursts of electrons precipitating into increasingly dense atmosphere. Research from 2012 showed that torches typically last less than 1 second and travel downward along magnetic field lines. High-speed cameras in Svalbard captured torches in 2015, measuring their velocities and brightness variations. Scientists noted that torch frequency increases during substorm onset. To think that light can appear to fall from the sky like rain, each drop an avalanche of electrons finding their way home to Earth. Auroral spirals form when incoming electrons interact with atmospheric winds, creating rotating structures that can span hundreds of miles. Imagine watching an aurora twist itself into a spiral pattern, rotating slowly like a cosmic hurricane made of light. Research from 1999 at the Norwegian Defence Research Establishment showed that spirals indicate regions where strong electric fields couple with neutral winds in the ionosphere. Scientists discovered in 2005 that spirals rotate at speeds between 1 and 5 miles per second. During the March 1989 storm, satellites captured massive spiral structures over Canada, some rotating clockwise and others counterclockwise. Time-lapse photography from Finland in 2017 showed a spiral aurora completing one full rotation in about 8 minutes. This reminds us that the atmosphere isn't merely a stage where auroras perform, but an active participant, shaping light with its invisible winds. The auroral breakup is the explosive onset of a substorm, when quiet arcs suddenly brighten by factors of 100 or more and fragment into rapidly moving forms. Imagine watching a gentle green arc hanging motionless in the northern sky when suddenly it explodes into motion, brightening to painful intensity in seconds. Scientists discovered in 1961 that Sidney Chapman first described this phenomenon as one of the most dramatic events in geophysics. Research from Themis satellites in 2008 showed that breakup begins at a specific point in the magnetic tail, then propagates both eastward and westward at speeds exceeding 500 miles per second. During breakup, quiet arcs transform into swirling coronas, racing rays, and pulsating patches in Fairbanks, Alaska. All sky cameras have documented breakups where the sky transitions from green to red to white in under 30 seconds. To think that stillness can explode into such fury with no warning, a reminder that peace often conceals energy waiting to be released. Diffuse aurora is a faint, structureless glow that covers large areas of sky, usually appearing as a soft green or red background behind discrete auroral forms. Picture a gentle luminescence washing across half the sky, bright enough to see but to diffuse to photograph well. Scientists discovered in 1977 that diffuse aurora is caused by electrons precipitating from the plasma sheet, a region of trapped particles in Earth's magnetotail. Research from 2009 showed that diffuse aurora actually contains more energy than discrete aurora but spreads it over much larger areas. During geomagnetic storms, diffuse aurora can cover more than 4 million square miles simultaneously. Spacecraft measurements in 2013 revealed that diffuse aurora deposits enough energy into the atmosphere to create winds exceeding 300 miles per hour at altitudes around 75 miles. This reminds us that what appears faint and insubstantial can contain more power than what dazzles our eyes. Quiet strength distributed across vast distances. Omega bands are large-scale undulations in auroral arcs that resemble the Greek letter omega, spanning hundreds of miles. Imagine watching an auroral arc develop massive curves and folds, like a ribbon laid across the sky by careless hands. Scientists discovered in 1984 that these bands indicate large-scale waves propagating through the magnetosphere-ionosphere system. Research from 2001 at the Finnish Meteorological Institute showed that omega bands typically move eastward at speeds between 0.3 and 1.5 miles per second. Each fold can span more than 200 miles from peak to trough. In March 2015, all-sky camera networks across Scandinavia captured a series of omega bands propagating across 3 countries, allowing scientists to track their motion and evolution. To think that light can form cursive script across continents, the sky writing letters in an alphabet we're still learning to read. Auroral flickering consists of rapid brightness variations occurring at frequencies between 3 and 15 Hz, near the limit of human temporal resolution. Imagine watching an aurora shimmer like a distant flame, its brightness pulsing faster than you can consciously count. scientists discovered in 1971 that these flickers are caused by modulation of electron precipitation by electromagnetic waves propagating along magnetic field lines. Research from 2017 using high-speed cameras showed that flickering auroras can brighten and dim completely in just 70 milliseconds. During intense displays, different parts of an auroral curtain can flicker at different frequencies simultaneously, creating complex patterns. In Sweden, researchers in 2019 synchronized high-speed cameras with magnetometer measurements, proving that each brightness pulse corresponds to a burst of electrons arriving from space. This reminds us that what appears steady to our eyes is actually pulsing, the universe operating on timescales faster than our perception allows. The southward displacement of the auroral oval during major geomagnetic storms has brought northern lights to locations as far south as the Caribbean. Imagine standing on a tropical beach and seeing green curtains appear above palm trees, an impossibility made real by solar fury. Historical records show that during the Carrington event of 1859, auroras appeared over Cuba, Jamaica, and the Bahamas. Research from 2003 analyzing the May 1921 geomagnetic storm found that auroras were visible from Samoa, nearly 14 degrees south of the equator. During the Halloween storms of October 2003, auroras appeared over Texas, Arizona, and Southern California simultaneously. Scientists estimated that during the most extreme solar storms, the auroral oval could expand to cover more than half of Earth's surface. To think that these lights know no permanent boundary, that given enough fury from the sun, they could dance above every place on Earth. Auroral prediction relies on measurements of solar wind and interplanetary magnetic field orientation taken by spacecraft positioned between Earth and the Sun. Imagine satellites stationed at Lagrange Point 1, hovering 930,000 miles from Earth, constantly monitoring the solar wind that will reach us in 30 to 60 minutes. NASA's ACE satellite has provided real-time solar wind data since 1997. Giving forecasters advance warning of approaching disturbances. Research from NOAA's Space Weather Prediction Center shows that auroral forecasts achieve approximately 75% accuracy for major events, but struggle with precise timing and intensity. During the St. Patrick's Day storm of 2015, satellites detected the arriving coronal mass ejection, but underestimated its strength, surprising forecasters with auroras visible from Scotland to New Zealand. This reminds us that despite our monitoring and mathematics, the sun still holds capacity for surprise, refusing to be entirely predictable. The auroral kilometric radiation mentioned earlier produces emissions so powerful they rank among the strongest radio signals in the solar system. Picture Earth screaming in radio frequencies during auroral storms, broadcasting with power exceeding 1 million watts, louder in radio than many cosmic sources we study with telescopes. Scientists discovered in 1985 that these emissions are generated by a process called cyclotron maser instability, where electrons spiraling along magnetic field lines produce coherent radio waves. Research from NASA's Van Allen probes in 2015 measured these emissions directly, finding peak intensities at frequencies around 300 kHz. Radio astronomers have detected similar emissions from Jupiter that are 10,000 times stronger than Earth's. In 2019, astronomers detected auroral radio emissions from a brown dwarf star 20 light-years away, the first time such emissions were detected beyond our solar system. To think that auroras sing to the cosmos in frequencies we cannot hear, Earth announcing its magnetic presence to anyone listening. The cost of geomagnetic storms to modern infrastructure is measured in billions of dollars annually. Imagine invisible currents flowing through power transmission lines, transforming them into antennae that pick up and amplify auroral electric fields. The March 1989 storm that darkened Quebec caused an estimated $13.2 million in direct damages and $100 million in lost revenue. Research from 2013 by Lloyd's of London estimated that an extreme geomagnetic storm today could cause $2.6 trillion in damages to the United States alone. During the Halloween storms of 2003, satellites lost functionality. GPS systems experienced errors up to 30 feet, and airline flights were rerouted away from polar regions to maintain radio communication. The Swedish power grid experienced widespread disturbances, and transformers in South Africa were damaged despite being far from polar regions. To think that beauty in the sky translates to cascading failures in our technological systems, that the same forces which inspire awe can dismantle the infrastructure we depend on. The electric field associated with auroras can reach 400 millivolts per meter during intense displays. Picture invisible forces strong enough to be measured with simple instruments, electric fields permeating the air beneath shimmering curtains. Research from 2016 showed that these fields can induce currents in long conductors, like pipelines, causing corrosion and requiring special protection systems. Scientists at the University of Tromsk measured in 2018 that during major geomagnetic storms, electric fields reached strengths capable of affecting animal navigation systems. In northern Finland, reindeer herders have reported unusual animal behavior during strong auroral displays, observations that correlate with measured electric field strengths. To think that the air itself becomes electrically alive, charged with forces that flow through everything, animate and inanimate alike. Some auroras emit X-rays strong enough to penetrate the atmosphere and reach aircraft altitudes. Imagine standing on the ground, looking up at green curtains, while above you invisible X-rays rain downward, created by electrons moving at a significant fraction of light speed. Scientists discovered in 2001 that the Pixie balloon experiment detected X-ray emissions from auroras at energies up to 100 keV. Research from 2017 showed that these X-rays are produced when extremely energetic electrons collide with atmospheric molecules at altitudes around 20 miles. During solar storms, airline crews flying polar routes receive elevated radiation doses equivalent to several chest X-rays per flight. This reminds us that beauty can carry invisible edges, that light shows can produce radiation we cannot sense but which passes through us nonetheless. The DST index measures the strength of geomagnetic storms using a scale where more negative numbers indicate stronger disturbances. Picture scientists around the world maintaining magnetic observatories that feed data into a single number, updated hourly, quantifying the storm in Earth's magnetic field. Research from Kyoto University, which maintains the DST index, shows that the Carrington event likely reached values below -1,760 The March 1989 Quebec blackout occurred during a storm reaching -589 nanoteslas. During the Halloween storms of 2003, the DST index reached -383 nanoteslas. Scientists consider any value below -100 to indicate a major geomagnetic storm. To think that we've reduced the fury of cosmic forces to a single descending number, mathematics attempting to contain chaos. The KP index divides Earth into latitude bands and rates auroral activity on a scale from 0 to 9. Imagine the planet sectioned like an onion, each layer assigned a number describing magnetic turbulence, forecasters using these numbers to predict where auroras will appear. Scientists developed this index in 1949 at the University of Göttingen, based on magnetic field variations measured every 3 hours. Research from NOAA shows that Kp values above 5 indicate auroral visibility at mid-latitudes, while Kp9 represents extreme storms with auroras visible near the equator. During the St. Patrick's Day storm of 2015, Kp reached 8, bringing auroras to England, Germany, and the northern United States. This reminds us that we've learned to speak the sun's violence in numbers, creating scales to measure what our ancestors saw as divine. The solar cycle follows an approximately 11-year pattern from minimum to maximum and back, though individual cycles vary considerably. Picture the sun's magnetic field flipping completely every 11 years, north becoming south, activity waxing and waning in a rhythm that governs auroral frequency. Scientists have tracked sunspot numbers since Galileo first observed them in 1610, creating a continuous record spanning more than 400 years. Research from NASA's Solar Dynamics Observatory shows that solar cycle 24, which peaked in 2014, was the weakest in a century. Solar cycle 25 began in December 2019 and is predicted to peak around 2025. During solar maximum, auroral displays occur 3 to 4 times more frequently than during minimum. To think that our star breathes with a rhythm measured in decades, a pulse so slow that no human witnesses more than 7 or 8 of its cycles. The Maunder minimum was a 70-year period from 1645 to 1715, when sunspot activity nearly ceased and auroral displays became extremely rare. Imagine generations living their entire lives in Europe with almost no auroral sightings, the skies darker than they'd been in centuries. Historical research published in 2003 analyzed astronomical records from the period and found fewer than 50 documented auroras compared to thousands in equivalent periods before and after. Scientists discovered that this minimum coincided with the Little Ice Age in Europe, though the exact relationship remains debated. Korean records from the Joseon dynasty show a similar decrease in auroral observations during these decades. To think that the sun can fall silent for human lifetimes, its fury suppressed by mechanisms we still don't fully understand. Auroral scientists use a classification system called the IBC scheme, rating displays by intensity, border structure, and color. Picture researchers in the 1960s watching time-lapse films of auroras, developing a taxonomy to describe what they saw, creating a language for light. The International Auroral Atlas, published in 1963, established standards that scientists still use today. Research from the Geophysical Institute shows that this classification helps correlate ground observations with satellite measurements. Intensity ranges from I4 weak to 4-4, very bright, structure from 1 for homogeneous, 2-4-4, pulsating, colors classified by dominant wavelength. This reminds us that science begins with naming, that to study something we must first agree on language to describe it. The solar wind's density averages about 5 particles per cubic centimeter, making it a better vacuum than anything we can create in laboratories on Earth. Imagine space between Earth and Sun, filled with matter so sparse that a volume the size of a sugar cube contains only a handful of atoms. Scientists measured in 1969 during Apollo missions that interplanetary space contains densities far lower than the best vacuums achieved in terrestrial laboratories. Research from the Parker Solar Probe in 2021 measured solar wind near the Sun's surface with densities reaching 5,000 particles per cubic centimeter, showing how it thins as it expands. Despite this extraordinary emptiness, the solar wind carries enough energy to power all auroral displays. To think that something nearly nothing can travel millions of miles and paint light across our sky. The bow shock is where solar wind first encounters Earth's magnetic field, creating a standing shockwave in space. Picture an invisible wall 50,000 miles from Earth, where supersonic wind suddenly slows to subsonic speeds. Matter piling up like water hitting a boulder. Scientists discovered in 1964 that the MP-1 satellite first crossed this boundary, measuring temperature jumps and density increases. Research from the Cluster mission in 2003 showed that the bow shock oscillates inward and outward by thousands of miles, breathing with variations in solar wind pressure. During the Halloween storms of 2003, the bow shock was compressed to within 20,000 miles of Earth, half its normal distance. To think that Earth wears a shockwave like armor, an invisible shield constantly hammered by stellar wind. The magnetopause is the boundary between Earth's magnetic field and interplanetary space, typically located about 40,000 miles toward the Sun. Imagine a membrane separating our magnetic bubble from the void, flexing inward during solar storms and relaxing outward during quiet periods. Scientists discovered in 1961 that NASA's Explorer 12 satellite first detected this boundary by measuring sudden changes in magnetic field strength. Research from the THEMIS mission in 2007 showed that the magnetopause can move by 25,000 miles during severe storms. During the Carrington event, scientists estimate the magnetopause was compressed to within 20,000 miles of Earth's surface. This reminds us that our planet's protective bubble is not solid but yielding, pushed and pulled by forces from the Sun. Plasma instabilities in the magnetotail cause it to snap like a whip, releasing stored energy in substorm onset. Picture the magnetotail stretching more than 200,000 miles behind Earth, accumulating energy like a drawn bow until instability triggers sudden release. Scientists discovered in 2008 that THEMIS satellites pinpointed where these instabilities begin, roughly 60,000 miles from Earth. Research showed that the magnetotail doesn't snap completely, but develops localized tears that propagate both toward and away from Earth. During substorm onset, energy equivalent to a magnitude 5.5 earthquake is released in space. In July 2013, spacecraft measured magnetic field lines in the tail, moving at speeds exceeding 600 miles per second during reconnection. To think that behind our planet, invisible forces build and break in cycles of hours, releasing power that could illuminate cities. The ionosphere becomes a better conductor during auroral displays, with electron density increasing by factors of 10 or more. Imagine the thin air 60 miles up suddenly swarming with free electrons, transforming from insulator to conductor in minutes. Scientists discovered in 1958 that radio waves behave differently during auroral activity because ionospheric conductivity changes. Research from 2010 showed that auroral electron precipitation can increase ionospheric conductivity from 0.1 to more than 10 Siemens per meter. During the March 1989 storm, conductivity reached values allowing currents exceeding 1 million amperes to flow through the auroral electrojet. This reminds us that the atmosphere isn't fixed but responsive, its properties transforming under bombardment from space. Auroral chemistry creates nitrogen oxides that can deplete ozone in the upper atmosphere. Picture auroras not just as light, but as chemistry happening in the sky. Energetic electrons breaking apart molecules and forcing them to recombine in new forms. Research from 2008 showed that during large solar storms, auroral production of nitrogen oxides increases by factors of 100. creating compounds that descend into the stratosphere over weeks. Scientists discovered in 2016 that major geomagnetic storms can temporarily reduce polar ozone by 1 to 2%. During the solar storm sequence in 2003-2004, satellite measurements detected significant ozone depletion over Antarctica. To think that beauty has consequences. That light in the sky writes chemical equations that change the composition of the air we breathe. The aurora at Jupiter creates radio emissions 10,000 times more powerful than Earth's auroral kilometric radiation. Imagine standing on one of Jupiter's moons and hearing nothing while around you. Radio waves scream at intensities that dwarf Earth's strongest broadcasts. Scientists discovered in 1979 that Voyager 1 first detected these emissions while still millions of miles from Jupiter. Research from the Juno spacecraft in 2017 measured peak radio powers exceeding 100 million watts. Jupiter's auroras are powered by its rapid rotation and volcanic moon, Io, which injects tons of material into Jupiter's magnetosphere every second. In 2016, Hubble captured ultraviolet images of Jupiter's auroras, revealing structures larger than Earth. To think that our planet's light shows are gentle whispers, compared to the roar of giant worlds. Saturn's auroras pulse with the rotation of the planet, creating unique, oval-shaped displays at both poles. Picture rings of light encircling Saturn's poles, brightening and dimming every 10.7 hours as the planet spins. Scientists discovered in 2004 that the Cassini spacecraft measured these regular pulsations in both visible and radio wavelengths. Research from 2011 showed that Saturn's auroras respond differently to solar wind than Earth's, sometimes brightening when solar wind pressure decreases rather than increases. During a solar storm in 2005, Cassini observed Saturn's aurora expanding by 50%, reaching closer to the equator. To think that each planet dances to its own rhythm, auroras reflecting not just solar wind, but the unique character of each world. Uranus's auroras appear in unexpected locations because the planet's magnetic field is tilted 59 degrees from its rotation axis. Imagine a world where auroras wander across the entire planet during each rotation rather than staying fixed at the poles. Scientists discovered in 2011 that the Hubble Space Telescope first detected Uranus's auroras in ultraviolet wavelengths. Research from 2017 showed that as Uranus rotates, its magnetic poles point almost directly at the Sun for part of each orbit, creating auroral configurations unlike any other planet. During Voyager 2's flyby in 1986, instruments detected radio emissions suggesting auroral activity, though cameras couldn't capture visible light. To think that a sideways world creates sideways auroras, light following magnetic fields that point in strange directions. The auroral zone is a band roughly 3 to 6 degrees wide in latitude that encircles each magnetic pole where auroras appear most frequently. Imagine a ring hovering above the Arctic, centered not on the geographic pole but offset toward northern Canada, a zone where auroras glow on more than 200 nights per year. Scientists at the University of Alaska established in 1963 that Fairbanks sits almost perfectly beneath this zone, making it one of Earth's premier auroral viewing locations. Research from 2014 using satellite data mapped the auroral zone's position throughout solar cycles, showing it expands equatorward during storms and contracts poleward during quiet periods. During solar maximum, the zone's southern edge shifts from roughly 67 degrees north to below 60 degrees, bringing auroras within view of millions more people. To think that there exists an invisible belt around Earth where the sky performs almost nightly, a theater of light with predictable geography. The plasma sheet is a region in Earth's magnetotale where hot charged particles accumulate before precipitating into the atmosphere during substorms. Picture a reservoir of energy stored tens of thousands of miles behind Earth, particles trapped and heated until conditions trigger their release. Scientists discovered in 1972 that the ISEE spacecraft first measured plasma sheet temperatures exceeding 50 million degrees Fahrenheit. Research from NASA's Themis mission in 2009 showed that the plasma sheet thins before substorm onset, compressed from 6,000 miles thick to less than 600 miles in under an hour. During this thinning, the sheet becomes unstable, triggering magnetic reconnection that hurls particles toward Earth. To think that behind our planet floats a lake of fire waiting to drain earthward, heat measured in millions of degrees, suspended in near vacuum. The ring current is a belt of charged particles encircling Earth at distances between 6,000 and 35,000 miles that intensifies during geomagnetic storms. Imagine a river of electricity flowing around Earth's equator, invisible and powerful, its current reaching millions of amperes during major storms. Scientists discovered in 1962 that this current creates a magnetic field opposing Earth's, temporarily weakening our planet's field by up to 2%. Research from the Van Allen probes in 2014 measured how energy stored in the ring current during storms takes days to dissipate after solar wind pressure decreases. During the March 1989 storm, the ring current's energy exceeded 1,015 joules, equivalent to the explosive power of 250 megatons of TNT. This reminds us that Earth wears invisible belts of energy, currents flowing through emptiness with power that could devastate cities if somehow brought to ground. Polar cap arcs are auroral forms that appear poleward of the main auroral oval, reaching across the magnetic pole itself. Picture ribbons of light stretching from dawn to dusk across the highest latitudes, appearing when most instruments predict no auroral activity. Scientists discovered in 1975 that these arcs occur during periods when the interplanetary magnetic field points northward, allowing solar wind entry through Earth's polar cusps. Research from 2018 using all-sky cameras at the South Pole showed that polar cap arcs can persist for many hours, slowly drifting across the polar cap. During geomagnetically quiet periods in 2016, cameras captured multiple parallel arcs spanning from Russia to Canada. To think that even the regions we thought protected from solar bombardment can glow with light. That Earth's magnetic fortress has gates at its crown. The cusp is a region near the magnetic poles where Earth's field lines open directly to interplanetary space, allowing solar wind particles direct access to the atmosphere. Imagine a funnel at each pole where solar wind pours in continuously, creating perpetual aurora-like glow even during geomagnetically quiet times. Scientists discovered in 1970 that satellites crossing the cusp measured sudden jumps in particle flux and turbulence. Research from the Cluster mission in 2005 showed that the cusp moves with solar wind pressure variations, its location shifting by several degrees in latitude within minutes. During solar storms, the cusp expands, allowing particles to penetrate to lower altitudes and latitudes. In Svalbard, Norway, observers at 78 degrees north frequently see daytime auroral activity caused by cusp precipitation. To think that our magnetic shield contains permanent openings, gates that can never fully close, where space weather pours through unimpeded. Field-aligned currents, also called Birkeland currents, flow along magnetic field lines, connecting the magnetosphere to the ionosphere. Picture rivers of electricity flowing vertically through space, carrying up to 1 million amperes between the magnetosphere and upper atmosphere. Norwegian scientist Christian Birkeland proposed these currents in 1903 based on his Tarella experiments, but the scientific community rejected his ideas for decades. Satellites finally confirmed their existence in 1966, vindicating Birkeland 28 years after his death. Research from 2001 showed these currents form circuits, with current flowing into the ionosphere on the dawn side and out on the dusk side. During substorms, these currents intensify by factors of 10, pumping energy from space into the atmosphere. To think that vindication can come too late for its discoverer, truth waiting decades to be acknowledged. Alpha-von waves are oscillations in magnetized plasma that carry energy from the magnetosphere into the ionosphere, accelerating auroral electrons. Imagine waves in an invisible ocean, ripples in magnetic fields that surf along field lines at speeds exceeding 600 miles per second. Swedish physicist Hans Alfvén predicted these waves in 1942, earning the Nobel Prize in Physics in 1974, his work in magnetohydrodynamics. Research from NASA's FAST satellite in 2002 measured Alfvén waves directly above auroral arcs, confirming they accelerate electrons to energies needed to create visible light. During intense auroral activity in 2015, the Themis spacecraft detected Alfvén waves with electric field amplitudes exceeding 50 millivolts per meter. To think that space behaves like an ocean with its own waves, invisible undulations carrying energy downward to paint our sky. The loss cone is a range of particle trajectories that lead to atmospheric collision rather than continued magnetic trapping. Picture a cone of angles pointing downward from each point in the magnetosphere, any particle moving within that cone destined to strike atmosphere and create aurora. Scientists calculated in 1957 that the loss cone's width depends on magnetic field strength and altitude, narrowing as particles move farther from Earth. Research from 2006 showed that wave-particle interactions constantly scatter trapped particles into the loss cone, maintaining steady auroral precipitation during substorms. The loss cone effectively widens as magnetic field lines reconnect, dumping previously trapped particles into the atmosphere in bursts. This reminds us that space contains invisible geometries of fate, angles that determine whether particles orbit forever or fall to become light. The ionospheric trough is a region of depleted electron density on the equatorward edge of the auroral zone. Imagine a valley carved into the ionosphere's electron population, a depletion zone where plasma density drops by factors of 10. Scientists discovered in 1963 that satellite measurements revealed this permanent feature circling the globe. Research from 2009 showed that the trough forms because strong electric fields in the auroral zone pull plasma toward the poles, leaving a depleted region behind. During geomagnetic storms, the trough moves equatorward with the expanding auroral oval, affecting radio communications across wider areas. In 2017, the Swarm satellite constellation mapped the trough's structure in 3 dimensions, revealing complex patterns. To think that auroras don't just add light, but subtract particles, carving emptiness in the sky's electron sea. Energetic, neutral atoms are created when charged particles in Earth's magnetosphere collide with hydrogen atoms, producing neutral particles that can escape magnetic confinement. Picture invisible particles racing away from Earth in all directions, carrying information about magnetospheric dynamics into interplanetary space. Scientists discovered in 2000 that NASA's IMAGE satellite first mapped Earth's magnetosphere by detecting these escaping neutral atoms. Research from 2012 showed that during geomagnetic storms, energetic neutral atom production increases dramatically, creating a detectable glow around Earth visible from deep space. The Swedish Institute of Space Physics developed instruments in 2005 that can image the entire magnetosphere by detecting these particles. To think that Earth leaks particles constantly, a quiet exhalation of neutral atoms carrying the signature of magnetic storms to the cosmos. The plasma pause is a sharp boundary in Earth's magnetosphere where plasma density drops by factors of 100 or more over distances of just a few miles. Imagine an invisible cliff in space, plasma abundant on one side and sparse on the other. The boundary moving inward during storms and outward during quiet times. Scientists discovered in 1963 that NASA's Explorer's satellites first detected this feature at altitudes around 12,000 miles. Research from the Van Allen probes in 2015 showed that the plasma pause forms because Earth's rotation creates electric fields that trap cold plasma close to the planet. During the March 2015 storm, the plasma pause compressed from 24,000 miles to less than 9,000 miles from Earth in under 6 hours. To think that space contains edges where abundance becomes scarcity across distances smaller than cities. Boundaries drawn by forces we cannot see. Chorus waves are electromagnetic oscillations in the magnetosphere that sound like birds chirping when converted to audio frequencies. Imagine radio telescopes detecting rising tones in space, sweeping upward in pitch like dawn birdsong, waves that accelerate electrons and contribute to auroral displays. Scientists discovered in 1969 that these waves were first recorded during the International Geophysical Year. Their distinctive rising tone pattern immediately recognizable. Research from NASA's Van Allen probes in 2014 measured chorus waves directly, showing they accelerate electrons from low energies to radiation belt energies in seconds. During substorms in 2016, the ERACE satellite recorded chorus waves with amplitudes strong enough to scatter trapped electrons into auroral precipitation. This reminds us that space has its own music, electromagnetic symphonies playing constantly in the void, conducting particles like invisible orchestras. Hiss is a type of plasma wave that creates steady background noise in the magnetosphere, unlike the chirping of chorus waves. Picture static in space, electromagnetic noise filling the magnetosphere like radio interference, damping particle energies and smoothing out sharp gradients. Scientists discovered in 1957 that early satellite measurements detected this steady emission at frequencies between 100 Hz and 10 kHz. Research from 2005 showed that plasmaspheric hiss plays a crucial role in clearing particles from the inner magnetosphere, preventing radiation belts from building to dangerous levels. During the recovery phase, after geomagnetic storms, hiss intensifies, gradually removing particles that storms injected into the inner magnetosphere. To think that nature employs noise as a cleaning mechanism, static that scrubs space of accumulated particle populations. The harangue discontinuity is a sharp boundary in the auroral oval where plasma flow reverses direction. Imagine standing beneath this invisible line where ionospheric winds shift from eastward to westward in less than 30 miles, creating shear that intensifies electric fields and brightens auroras. Norwegian scientist Liv Harang discovered this feature in 1946 by analyzing magnetic field measurements from observatories across Scandinavia. Research from 2008 using super-DAR radars showed that the discontinuity marks where magnetospheric convection patterns divide. During substorms, auroral brightening often begins at or near the Harang discontinuity. In 2013, the swarm satellites crossed this boundary and measured electric field changes exceeding 40 millivolts per meter across distances of just 6 miles. To think that the aurora contains internal borders, places where flows collide and energy concentrates. The radiation belts were discovered in 1958 by instruments aboard Explorer 1, surprising scientists with regions of intense, trapped radiation encircling Earth. Imagine zones of deadly radiation starting about 600 miles up and extending beyond 36,000 miles. Particles so energetic they could kill an unprotected human in hours. James Van Allen analyzed the data and realized Earth was surrounded by populations of high-energy particles trapped by the magnetic field. Research from the Van Allen probe's mission in 2013 discovered a third, temporary radiation belt that appears during certain geomagnetic conditions. During solar storms, these belts swell with additional particles, threatening satellites that orbit within them. To think that one of the first discoveries of the space age was that Earth wears belts of deadly radiation. Protection and danger mingled in the same magnetic architecture. South Atlantic anomaly is a region where Earth's magnetic field dips closer to the surface, allowing radiation belt particles to penetrate to lower altitudes. Picture a weak spot in our magnetic shield over Brazil and the South Atlantic, where the field strength is 30% weaker than at equivalent latitudes elsewhere. Scientists discovered in 1958 that this anomaly causes satellites to receive elevated radiation doses when passing through the region. Research from NASA in 2020 showed that the anomaly is growing and drifting westward at about 12 miles per year. The International Space Station experiences most of its radiation exposure while passing through this region. Astronauts report seeing random flashes of light caused by high-energy particles striking their retinas during these passes. This reminds us that Earth's shield contains thin spots, regions where space reaches closer to the ground. The ionospheric α1 resonator is a cavity between the ionosphere and magnetosphere, where electromagnetic waves can bounce back and forth. Picture waves trapped between two mirrors, one formed by the dense ionosphere below and another by changing plasma properties above, resonating at frequencies between 0.1 and 10 Hz. Scientists discovered in 1984 that ground-based magnetometers detected these resonances as oscillations in magnetic field measurements. Research from 2007 showed that the resonator's properties change during auroral activity, its resonant frequencies shifting with ionospheric electron density. During substorms in 2015, researchers detected strong resonances that persisted for hours after visible auroral activity subsided. To think that above us exists an invisible musical instrument, a cavity that vibrates with electromagnetic tones following the laws of wave mechanics. Polar mesospheric clouds, also called noctilucent clouds, can become more visible during periods of enhanced auroral activity. Imagine ice crystals forming at altitudes around 50 miles, Earth's highest clouds, glowing blue-white in summer twilight. Their formation influenced by water vapor created when auroral particles break apart methane molecules. Scientists discovered in 1885 that these clouds first appeared in the years following the Krakatoa eruption, though their connection to auroral activity wasn't established until the 1970s. Research from NASA's AIM satellite in 2018 showed that solar minimum periods with fewer auroral events correlate with reduced noctilucent cloud frequency. During the solar maximum of 2001-2002, observers reported increases in noctilucent cloud sightings at lower latitudes. This reminds us that auroras leave traces beyond light, their chemistry seeding clouds at the edge of space. Ground-induced currents flow through Earth's surface during geomagnetic storms, following paths of least resistance through rock and soil. Picture invisible rivers of electricity flowing through the ground beneath your feet during auroral displays, seeking out pipelines, railway tracks, and power lines. Scientists discovered in 1972 that the Trans-Alaska Pipeline required special protection systems after engineers found that geomagnetically induced currents caused accelerated corrosion. Research from 2015 showed that bedrock conductivity determines where these currents flow strongest, with regions of conductive rock experiencing higher current densities. During the March 1989 storm, ground currents in Canada exceeded 300 amperes, flowing through rock with resistance that would normally prevent such currents. To think that auroral electricity doesn't stop at the surface, but penetrates deep into Earth, seeking ground through stone itself. The Arctic tern migrates between polar regions annually, potentially experiencing more auroral displays than any other creature. Imagine a bird that sees summer sun at both poles, flying 25,000 miles each year, passing through auroral zones multiple times during each journey. Scientists discovered in 2010 that tracking devices revealed Arctic terns don't fly directly between poles, but follow meandering routes that keep them over productive ocean waters. Research from 2016 showed that during migration, terns fly through auroral zones during both spring and autumn, potentially witnessing displays in both hemispheres within weeks. Some individuals live more than 30 years, potentially witnessing thousands of auroral events across their lifetime. To think that a bird weighing less than 5 ounces sees more of Earth's magnetic light shows than most humans ever will. A life spent commuting between the planet's crowned poles. The substorm expansion phase typically lasts 30 to 60 minutes, during which auroral activity reaches maximum intensity before gradually declining. Picture the sky exploding into motion, brightening from quiet green arcs to violent coronas filled with racing rays, then slowly fading back toward calm over the course of an hour. Scientists discovered in 1968 that Cyanoche Akasofu divided substorms into distinct phases: growth, expansion, and recovery. Research from the Themis mission in 2009 measured how magnetic energy accumulates during the growth phase at rates exceeding Ya watts, then releases explosively during expansion. During the expansion phase, on March 13, 1989, auroral brightness increased by factors exceeding 1,000 in under 5 minutes across Alaska and northern Canada. To think that the sky's fury follows a predictable schedule, violence that announces itself and retreats according to physical law rather than chaos. The recovery phase of a substorm can last several hours as the magnetosphere-ionosphere system returns to its pre-substorm state. Imagine the aftermath of an auroral explosion. The sky still glowing, but gently now. Energies dissipating through electromagnetic hiss and particle precipitation. The system exhaling after holding its breath. Research from 2011 at the University of Leicester showed that during recovery, the plasma sheet refills with particles from the solar wind, preparing for the next substorm cycle. Scientists measured in 2014 that energy dissipation during recovery occurs through multiple pathways: Joule heating in the ionosphere, particle precipitation, and electromagnetic radiation. During the recovery phase following the October 2003 substorms, satellites detected the plasma pause, gradually moving outward over 8 hours, returning to its pre-storm position. This reminds us that even cosmic systems need rest, time to restore balance after expenditure of accumulated energy. Transpolar arcs are auroral features that stretch across the polar cap, connecting dawn and dusk sides of the auroral oval. Picture a bridge of light spanning the Arctic, thousands of miles long but only 60 miles wide, appearing when solar wind conditions create unusual magnetic field configurations. Scientists discovered in 1982 that Defense Meteorological Satellite program images first captured these features from space. Research from 2005 showed that transpolar arcs form when the interplanetary magnetic field has a strong northward component, allowing magnetic reconnection at unusual locations. During January 2015, all sky cameras across Greenland captured a transpolar arc that persisted for more than 5 hours, slowly drifting across the pole. To think that auroras can build bridges across the most remote regions of Earth, connecting opposite horizons with ribbons of light. The westward traveling surge is a bright auroral bulge that moves westward at speeds up to 6 miles per second during substorm expansion. Imagine a wave of light rolling across the sky like a luminous tsunami, brightening everything in its path, leaving enhanced aurora in its wake. Scientists discovered in 1966 that this surge marks the most dynamic phase of substorm expansion, correlating with maximum energy dissipation. Research from 2010, using networks of all sky cameras, showed that the surge can travel more than 1,200 miles westward before dissipating. During the March 1989 storm, the westward traveling surge was visible from Alaska to Hudson Bay, a wave of light crossing 3,000 miles of northern sky in under 20 minutes. This reminds us that auroral features aren't stationary but mobile, light structures that travel faster than jets fly. Auroral forms can create shadows on clouds below them during extremely bright displays. Picture standing beneath an intense aurora, bright enough that clouds passing under it cast shadows on lower cloud layers. Light from 60 miles up, strong enough to create earthly shadows. Scientists documented in 1910 that Norwegian observers during the Great Auroral Display of October 1905 reported seeing their own shadows cast by auroral light. Research from 2003 analyzed historical accounts and determined that auroras must reach brightness levels exceeding -3 magnitude, comparable to Venus at its brightest, to cast noticeable shadows. During the Bastille Day storm of July 2000, observers in northern Canada reported auroras bright enough to read by, with visible shadows cast on snow. To think that something happening at the edge of space can become bright enough to paint shadows at ground level. Atmospheric light rivaling celestial sources. The ionospheric dynamo is a current system driven by atmospheric winds pushing charged particles across magnetic field lines. Imagine winds in the ionosphere acting like a generator, moving conductive plasma through Earth's magnetic field and creating electric currents that flow constantly even without auroral activity. Scientists discovered in 1882 that Balfour Stewart first proposed this mechanism to explain daily variations in Earth's magnetic field. Research from 2009 using satellite measurements showed that the dynamo generates currents exceeding 100,000 amperes during daytime when solar heating creates strong atmospheric winds. During geomagnetic storms, auroral currents overwhelm the dynamo currents, but during quiet periods, the dynamo dominates ionospheric current systems. This reminds us that Earth's atmosphere is always conducting electricity, winds creating currents through the simple act of motion through magnetic fields. The magnetic midnight is the time when a location passes through the center of Earth's magnetale, typically when substorms are most likely to begin. Picture an invisible clock written in magnetic coordinates, where midnight isn't determined by sun position, but by alignment with Earth's stretched magnetic field. Scientists discovered in 1970 that substorm onset shows strong preference for magnetic midnight plus or minus 2 hours. Research from 2007, analyzing thousands of substorms, confirmed that roughly 70% begin within this time window. During September 2017, researchers in Scandinavia documented 12 substorms over 5 days, with 10 beginning within 90 minutes of magnetic midnight. To think that Earth's magnetic geometry creates its own schedule, timing favoring certain hours when configuration makes energy release most probable. Discrete auroral arcs can remain stationary for hours, hanging in the same position while solar wind conditions stay constant. Imagine a curtain of green light fixed in the northern sky like a painted feature, not moving or flickering, present when you look away and still there when you return. Scientists discovered in 1974 that these quiet arcs mark locations where magnetospheric convection boundaries intersect the ionosphere. Research from 2003 showed that some quiet arcs persisted for more than 8 hours during periods of steady solar wind. During January 2019, time-lapse cameras in Iceland captured a discrete arc that remained in the same position for 6 hours, barely moving while stars wheeled around it. This reminds us that not all auroras dance, that sometimes they simply exist, marking boundaries in space with patient light. The equator-word boundary of the auroral oval marks where closed magnetic field lines end and stretched field lines begin. Picture an invisible border in the sky where Earth's dipolar field transitions to the wind-swept magnetotail. Particles on one side trapped and on the other escaping. Scientists discovered in 1977 that satellites could identify this boundary by measuring sudden changes in particle populations and magnetic field configuration. Research from 2012 showed that during storms this boundary moves equatorward as the magnetosphere compresses, bringing auroras to lower latitudes. During the Halloween storms of 2003, the boundary reached 35 degrees magnetic latitude, allowing auroras to be visible from Mediterranean regions. To think that what appears as the edge of auroral light is actually a fundamental boundary in Earth's magnetic architecture, separating regions where field lines have different fates. Alphavenic aurora is a type of discrete aurora characterized by small-scale structures and rapid variations. Imagine auroral curtains filled with fine vertical striations, each ray flickering independently, the entire display shimmering like wind-blown silk with structure down to scales of 300 feet. Scientists discovered in 1998 that these auroras are powered by alphavon waves carrying electric fields parallel to magnetic field lines. Research from the FAST satellite in 2002 measured electric fields exceeding 200 millivolts per meter associated with these auroras, accelerating electrons in narrow beams. During February 2014, high-speed cameras in Norway captured alphavenic aurora, with individual rays appearing and disappearing in under 0.1 seconds. To think that some auroras are powered not by steady particle beams but by electromagnetic waves, light flickering to the rhythm of plasma oscillations. The dayside aurora is a continuous source of auroral light that glows constantly in sunlit polar regions. Imagine the sun rising on the Arctic to reveal aurora already present, glowing green against the blue dawn sky, light that never stopped even when sunlight made it invisible. Scientists discovered in 1965 that all sky cameras operating during Arctic summer detected auroras at all local times. Research from 2008 showed that dayside aurora is caused by particles entering through the magnetic cusps, creating precipitation that continues regardless of substorm activity. During June 2015, cameras in Svalbard captured dayside auroras visible against the midnight sun, faint green bands competing with 24-hour daylight. This reminds us that auroras don't wait for darkness, they glow continuously, merely hidden by the brightness of day. patient light that darkness reveals rather than creates. The auroral horn is a region of enhanced precipitation on the dawn side of the auroral oval, where particles flowing from the magnetotail enter the atmosphere. Picture a concentrated funnel of particles descending into the atmosphere near dawn, creating reliably bright auroras at the eastern edge of the auroral zone. Scientists discovered in 1988 that satellite observations revealed this persistent feature where particle flux exceeds surrounding regions by factors of 2 to 5. Research from 2006 showed that the horn forms because magnetospheric convection preferentially delivers particles to this location. During substorms in March 2013, cameras in eastern Canada captured the auroral horn brightening dramatically while western regions remained relatively quiet. To think that dawn in magnetic coordinates brings its own reliable light show, particles announcing morning in their own way. Precipitating electron energy determines the altitude where auroras glow brightest. Imagine electrons arriving with different energies, choosing their own death altitudes. High-energy particles penetrating deeper before collision, low-energy particles stopping higher up. Scientists calculated in 1963 that 1 keV electrons deposit their energy around 75 miles altitude, while 10 keV electrons reach 50 miles before stopping. Research from 2009 using ground-based spectrometers showed that during substorms, average electron energy increases from 2 keV to more than 10 keV within minutes. During intense storms in October 2003, rocket measurements detected electrons exceeding 100 keV, reaching altitudes below 40 miles. This reminds us that invisible energies determine visible heights, that the spectrum of arriving particles sorts itself into vertical layers of light. The hydrogen arc is a faint proton aurora that appears equatorward of the main electron aurora as a featureless red glow. Picture a gentle red luminescence spread across the southern horizon, easily missed in photographs but visible to dark-adapted eyes, created by hydrogen atoms that began as protons in the solar wind. Scientists discovered in 1971 that these auroras emit primarily in the hydrogen bomber alpha line at 656.3 nanometers. Research from 2004 showed that proton auroras often span wider latitude ranges than electron auroras, but with much lower intensity. During the St. Patrick's Day storm of 2015, observers in Scotland reported faint red glows covering the entire northern horizon, likely hydrogen arcs extending to unusually low latitudes. To think that the lightest element announces its presence with its own color, hydrogen glowing red while oxygen creates green, each element broadcasting its identity in specific wavelengths. The ionospheric outflow is a continuous stream of ions flowing from Earth's ionosphere into the magnetosphere. Imagine our atmosphere leaking upward. Oxygen and hydrogen ions accelerated by electric fields until they escape ionospheric confinement, replacing some of the plasma Earth's magnetic field contains. Scientists discovered in 1982 that the Dynamics Explorer satellite measured significant ion outflows at auroral latitudes. Research from 2012 showed that during geomagnetic storms, outflow rates can exceed 1,026 ions per second, enough mass to fill an Olympic swimming pool in about 100,000 years. During the March 2015 storm, the swarm satellites measured oxygen ion outflows with velocities exceeding 12 miles per second. This reminds us that Earth breathes in both directions, solar wind entering while terrestrial atmosphere escapes, our planet exchanging matter with space in an eternal cycle. The Pedersen conductivity measures how easily current flows perpendicular to magnetic field lines in the ionosphere. Imagine the ionosphere as a resistor whose resistance changes with electron density, allowing more current to flow during auroral activity when free electrons become abundant. Scientists discovered in 1963 that Pedersen conductivity increases by factors of 10 or more during intense auroral precipitation. Research from 2010 showed that this conductivity enhancement allows the ionosphere to short-circuit some of the electric fields that drive auroral particle acceleration, creating feedback loops. During March 1989, ionospheric Pedersen conductivity in the auroral zone reached values exceeding 20 Siemens, allowing massive currents to flow with relatively small driving voltages. To think that the sky becomes more conductive when bombarded by particles, that it responds to assault by becoming more accommodating to current flow. The Hall conductivity measures how icily current flows perpendicular to both magnetic field and electric field in the ionosphere. Picture currents taking a sideways path, deflected by magnetic forces, flowing at right angles to the electric fields that drive them. Scientists established in 1962 that Hall conductivity in the ionosphere typically exceeds Pedersen conductivity by factors of 3 to 5. Research from 2008 showed that the auroral electrojet flows primarily as Hall current, with charges drifting eastward and westward depending on electric field direction. During substorms in January 2014, magnetometer arrays measured how Hall currents create magnetic field disturbances on the ground, their signature distinct from Pedersen currents. This reminds us that electricity in magnetized plasma doesn't flow in straight lines but follows the geometry of crossed fields, taking sideways paths that obey their own vector mathematics. Particle bounce motion occurs when charged particles spiral along magnetic field lines, reflecting at low altitudes where field strength increases. Imagine an electron starting near the equator, spiraling northward along a field line, approaching the Arctic, slowing as the magnetic field intensifies, finally reversing direction and spiraling back toward the equator. Scientists calculated in 1958 that electrons with energies of 10 keV complete this bounce cycle in about 2 seconds. Research from 2013 using the Van Allen probes showed that during geomagnetic storms, particles can bounce between hemispheres dozens of times before scattering into the loss cone. During quiet periods, some particles bounce for hours or days before precipitating. To think that particles play ping-pong with our atmosphere, bouncing between hemispheres until some interaction finally sends them falling as light. The drift motion of charged particles around Earth creates the ring current, with protons drifting westward and electrons drifting eastward. Picture invisible rivers of particles circling Earth's equator in opposite directions, their motion driven by gradients in magnetic field strength, completing circuits in minutes to hours depending on energy. Scientists discovered in 1961 that this drift motion separates charges, creating an electric current even though individual particles follow curved paths. Research from 2015 showed that 100 keV protons complete one orbit around Earth in about 10 minutes, while electrons at the same energy drift in the opposite direction, completing circuits in about 5 minutes. During the Halloween storms of 2003, the ring current intensified as particles were injected from the magnetotail, increasing drift speeds and current magnitude. To think that our planet wears two invisible rivers flowing in opposite directions, matter circling endlessly in paths determined by charge and magnetic geometry. The velocity filter effect occurs when crossed electric and magnetic fields allow only particles of specific velocities to pass through without deflection. Imagine the magnetosphere acting as a sorting machine, electric fields pushing particles one direction while magnetic forces push the opposite way. Only particles moving at precise speeds experiencing balanced forces. Scientists discovered in 1972 that this mechanism helps explain why certain particle populations appear at specific locations in the magnetosphere. Research from 2009 showed that the velocity filter operates most effectively in the plasma sheet boundary layer. During substorms in April 2016, satellites measured how particles with energies between 1 and 3 keV preferentially entered specific magnetic local time sectors while other energies were deflected. This reminds us that space contains invisible gates that select particles by velocity, electromagnetic customs checkpoints where speed determines passage. Pitch angle is the angle between a particle's velocity vector and the local magnetic field direction, determining whether the particle will precipitate or remain trapped. Picture an electron's corkscrew path, sometimes spiraling tightly around field lines, sometimes making wide, lazy loops, the tightness of that spiral determining its fate. Scientists established in 1960 that particles with pitch angles near 90 degrees tend to remain trapped, while those with small pitch angles precipitate quickly. Research from 2005 showed that wave-particle interactions constantly scatter particles in pitch angle, transferring some from stable orbits into the loss cone. During substorms in July 2013, measurements showed that particles scattered from high pitch angles to low ones in under 10 seconds, triggering sudden auroral brightening. To think that survival or death for a particle hinges on a single angle, geometry deciding whether it orbits for hours or falls in seconds. The mirror point is the location along a field line where a bouncing particle reverses direction, reaching minimum altitude before heading back toward the opposite hemisphere. Imagine billions of particles reaching their turning points simultaneously, creating a layer where particle density peaks, an invisible boundary where descent becomes ascent. Scientists calculated in 1959 that mirror point altitude depends on pitch angle, with particles having larger pitch angles mirroring at higher altitudes. Research from 2011 showed that for electrons creating visible aurora at 60 miles altitude, mirror points typically occur between 50 and 75 miles. During intense precipitation in October 2003, rocket measurements detected sharp increases in particle flux at mirror point altitudes. This reminds us that space contains turning points written by magnetic force, elevations where particles must reverse their journey. The plasmasphere is a region of cold, dense plasma extending from Earth's ionosphere to altitudes around 12,000 miles. Picture a torus of plasma rotating with Earth, composed mainly of hydrogen and helium ions at temperatures around 5,000 degrees, orders of magnitude colder than surrounding magnetospheric plasma. Scientists discovered in 1963 that radio wave measurements revealed this region of enhanced plasma density correlating with the planet. Research from 2006 showed that the plasmasphere takes days to refill after being depleted during geomagnetic storms. During quiet periods before March 2015, the plasmasphere extended beyond 24,000 miles, but within 12 hours of storm onset, it eroded to less than 10,000 miles. To think that Earth drags a cloud of plasma with it as it rotates. A correlating atmosphere at altitudes where the neutral atmosphere has long since vanished. Whistler waves are electromagnetic, oscillations that propagate along magnetic field lines, dispersing in frequency as they travel. Imagine radio waves launched by lightning traveling upward along field lines, spreading out in frequency so that high frequencies arrive before low ones, creating descending tones when converted to audio. Scientists discovered in 1953 that LRO story explained how these waves propagate through the magnetosphere. Research from 2008 showed that Whistler waves play crucial roles in scattering radiation belt particles into auroral precipitation during thunderstorms over North America in June 2014. Satellites detected whistlers that originated in lightning strikes and propagated to the opposite hemisphere, bouncing between conjugate points. This reminds us that lightning doesn't stop at the ionosphere but sends signals through space. Electromagnetic messengers carrying information about storms to the opposite side of Earth. The plasma pod's surface can develop plumes during geomagnetic storms, with narrow channels of dense plasma extending toward the magnetopause. Picture fingers of dense plasma reaching outward from the main plasmasphere, drawn by convection electric fields, stretching tens of thousands of miles toward the dayside magnetopause. Scientists discovered in 2001 that the image satellite's extreme ultraviolet imager first revealed these plume structures. Research from 2014 showed that plumes can persist for many hours, slowly rotating with Earth while being eroded by interactions with hot magnetospheric plasma. During the March 2013 storm, multiple satellites observed a plume extending from 18,000 miles altitude to beyond 42,000 miles. To think that our plasma cloud can develop tentacles during storms, reaching toward the boundary between terrestrial and solar domains. Magnetic local time is a coordinate system where noon always faces the sun and midnight always points away, regardless of Earth's rotation. Imagine a clock written on the magnetosphere, noon at the subsolar point, midnight in the magnetotail, slowly rotating relative to geographic coordinates as Earth spins. Scientists established this coordinate system in the 1960s to describe magnetospheric processes independently of Earth's rotation. Research from 2007 showed that many magnetospheric phenomena show strong organization in magnetic local time, with substorms preferring midnight sector and dayside reconnection occurring near noon. During storms in September 2017, auroral onset times converted to magnetic local time showed clustering around 23 o'clock MLT, despite occurring at different universal times. This reminds us that space physics writes its own clock, time measured not by Earth's rotation but by alignment with the Sun. The auroral acceleration region extends from about 1,200 to 8,000 miles altitude, where parallel electric fields accelerate electrons downward. Picture a vertical span of space where electric forces overcome magnetic trapping, pulling electrons toward Earth, imparting energies that will create visible aurora when they strike atmosphere. Scientists discovered in 1977 that the S3-3 satellite measured strong, parallel electric fields at these altitudes during auroral activity. Research from 2002 using the FAST satellite showed that these acceleration regions can develop electric potential drops exceeding 10,000 volts across vertical distances of just 600 miles. During substorms in November 2015, rockets launched through acceleration regions measured electric fields reaching 400 millivolts per meter aligned with magnetic field direction. To think that above the aurora exists an invisible accelerator, electric fields pulling particles downward with forces strong enough to make them glow. The ionospheric Alphen resonator can trap electromagnetic energy for extended periods, creating standing wave patterns. Imagine a cavity between ionosphere and magnetosphere ringing like a bell after being struck. Energy bouncing between boundaries, creating waves that persist for minutes. Scientists discovered in 1990 that this resonator has multiple resonant modes, each with characteristic frequency. Research from 2012 showed that lightning strikes can excite these resonances, with energy propagating globally through the resonator. During substorms in August 2016, magnetometers detected resonant oscillations at frequencies between 0.5 and 4 Hz that persisted for more than 20 minutes after auroral onset. This reminds us that the gap between atmosphere and space acts as musical instrument, responding to strikes with sustained tones at favored frequencies. The double oval structure has been observed during extreme solar wind. Pressure pulses when magnetospheric compression creates two distinct precipitation regions.